In the first question, we have a single slit given, distance d to the screen, and we're asked to find which of the following changes carried out separately will result in an increase in width of the first diffraction maximum. So this is the condition given. By the first diffraction maximum, the question means the width of the central bright fringe. So basically the width of that region seen on the screen. So we're looking at B and D. We know from this formula that if I increase B, I decrease the angle. So if I decrease this angle, the central bright will also get smaller. Since we want an increase in the width of this first diffraction maximum, we should choose a decrease in B to increase the width of the central bright fringe. As for the D, the distance to the screen, I'm going to demonstrate the screen position with this pencil. Without changing B and wavelength, the angle will not change. And in this pattern, if the screen is closer, see that the central bright is going to be smaller. If the screen is further, the width of the central bright gets bigger. So we need to choose an increase in D. This is answer A. Question number 2 is asking which of the following graphs best represents how the intensity I of the diffracted light varies with the diffraction angle theta. This is the shape of the graph that we expect, which is given in option C. Question number 3 gives us two diagrams of the diffraction patterns obtained on a screen far from the slit. In the top diagram, the wavelength is λ1 and the slit width is b1. And in the bottom diagram, the wavelength of light is λ2 and the slit width is b2. In each experiment, the distance between the slit and the screen is the same. Now, we don't know the relationship between the wavelengths. We don't know the relationship between the slit widths. All we do know is what the screen looks like. And this shows a smaller central bright, therefore a smaller angle for the top diagram, and a larger angle, so a larger central bright for the bottom diagram. Since the relationship between these three variables is given as that, and all we know is the relationship between the angles, that actually means that the angle is bigger on the bottom diagram, which allows us to deduce that that ratio is larger than that ratio. We cannot individually compare the wavelengths or the B's because they can both be the cause of this angle being larger than the first angle, but we can say that lambda over B ratio is bigger for the bottom diagram, which is given in option A. Question number 4 gives us a diagram where radiation from a microwave transmitter passes through a narrow single slit, and a receiver is placed several meters beyond the slit. In this case, the receiver is acting as the screen. The receiver can be moved between points A and B across the screen. So on the axis below, sketch a graph to show the variation of intensity of the microwave radiation along the screen. For this, your diagram has already been started and you're asked to complete the diagram. This is very straightforward, but it's a 3-mark question. So what do you need to watch for? One thing you have to watch for is that the intensity of the next maximum after the central maximum is very small. You should show 2 on either side and make sure they're equally spaced. The third thing you should watch for is that after every maxima, the graph touches the horizontal axis. In part 2, we are asked to explain 2 effects on the intensity distribution that was shown in part AI. So this is a 4-mark question. Two effects and two explanations. The first effect of the condition given, which is the width of the narrow slit being reduced. So this question is reducing B. Since we know reducing B means an increase in the diffraction angle, that would cause the central maximum to become wider. You can give a mathematical explanation here that the angle is inversely proportional to B. The second effect that would be seen on the screen will be that the pattern will get dimmer, in other words, less intense. There is larger energy incident on the screen when the single slit is wider. So the first part asks us to describe what is meant by diffraction of light. This is a 2-mark question. You need to say that diffraction means spreading out of light by an obstacle or through a gap. Either one of these would work. Part 2 gives us the diagram and asks us to sketch a graph to show how the intensity I varies from point C given on the screen. So you draw the single slit intensity pattern graph. This is a 3-mark question. Things to watch for is symmetry, graph being drawn to 0 over here and here, and intensity of the central max much larger than the next max. So make sure this is much larger than that. Part 3 asks us a calculation of the width of the central maximum. So it's asking for that whole length. Now we know the wavelength, we know B, and we know the distance from the screen, which is given as 1.9 meters. Using this information, I can calculate the angle, but how am I going to calculate the width of the central maximum? I'm going to use the fact that small angle approximation allows us to estimate that ratio is equal to that ratio when you label that distance as y. So the width of the central maximum would be 2y. So if the slit was here, that would be the angle to the first minimum from a 0 angle, and the opposite side would be y for this angle, and the adjacent side would be d. So this really comes from the small angle approximation, like I said, sine theta being equal to tangent theta. So the rest is substitution, and when you calculate, you find 2y to be equal to 5.9 times 10 to the minus 3 meters.